Thank you. So it's my great honor to be here to present my work. So also I'm a co-founder of a startup company called Kelvin Fu. So my research lab and also my startup company are focusing on developing, we call this world only 3D printer to enable the continuous fiber reinforced thermoset composites. So this is my topic, and also our technology, our 3D printer got the winner of 2020 ChemX Award. So this is a very important award in composites area. And also I belong to this Center for Composite Materials. So we have around half a century history in composites area. So next. Next. Okay. So this is my motivation and background. So why we need to work on composites? Because when you look outside, for the airplanes, for lots of the large-scale composite materials, actually we are using composites. But those composite materials are actually using thermoset resin, for example, like epoxy. So lots of thermoplastic materials cannot be used for the large-scale and also structural application because of the very poor mechanical properties and also very limited surface temperature to enable high-performance application. But if we look at those companies who are making composites, or they call this composites, but actually in my opinion, we don't believe they are making composites, because when we evaluate composites, a few factors we need to consider. The first one is fiber volume fraction. Okay, so normally only 50% or 60% by volume of fiber in the matrix can be considered as a composites, especially for the aerospace grade composites, the material. So if we want to achieve very high mechanical strength, that will require, we put a lot of continuous fiber in the materials. So in that case, we will see that. So the thermoset, or we call this epoxy 3D printing for composites, actually has not been developed yet. Because a lot of people, they are still using the UV resin to do the printing. But UV resin, they have a poor mechanical strength as well, and also limited mechanical property, and also the cross-linking density is pretty low. So if you shine the light to the UV resin, actually the UV light cannot penetrate through the very thick carbon fiber, okay, or other fiber materials. So that causes a limitation. And also, if we look at this diagram, so the only way to introduce high performance of composites is to use continuous reinforced carbon fiber plus thermoset. Okay, so here is our work. So we want to understand the challenges and develop a mechanism to solve these problems. So everyone talking composites, but why epoxy 3D printing is so challenging? So here I summarize a few challenges here. First one is the viscosity. Even though we call it thermoset, but it doesn't mean that if you apply the heat, the material will get cured or solidified. That's because if you look at this viscosity curve, the red line, so when you apply the heat, the viscosity will decrease significantly. Okay, that will make it trouble, to cure and form or retain the geometry during the printing. And also the curing time, if you look at the curing times, so that's around 400 minutes. A few hours. So normally we cannot wait until several hours to print a short period composites, under the printer head. And also most importantly, so the other one is the interface. So suppose that if we can cure the fiber or the resin instantly, okay, we place one layer. So this one layer, all the monomers has been cross-linked. So if we place another layer on the top, so the top layer cannot form a cross-linking, network with the bottom layer. So this is well known. So that's why if we do any type of layer-by-layer printing, so this material will have a very weak interlaminar bonding strength in between. Okay, so that's the two major challenges I think prevent the current development of 3D printing of composites. So here, so we developed this mechanism to solve the problem. So the first one is, we introduced the epoxy impregnation system to enable the fast resin impregnation. And also we call this in situ toe preg formation. So that means you give the dry fiber, so you can purchase from, Toray this company and put the dry fiber, and this dry fiber can get impregnated with any type of highly viscous resin to form the top prag. So this top prag is in the wet state, so it can be used for the following printing. So the second part, the second innovation is the dual cure resin coating. So we developed a dual cure resin. So this resin contains epoxy and UV polymers. So they can form an interpenetrating polymer network. So this interpenetrating polymer network can help to address the interfacial cross-linking problems. And also they could cure by the UV light to retain the 3D geometry. And once the part is done, so we can do the post-cure in the oven or any type of, some of the radiation process to form a very strong cross-linking of epoxy in between. So that's our printing mechanism. So here I want to show you a video to show that the demonstration of our process. So this shows the top prag with dual cure cladding. So the top prag is very flexible, but with the help of the surface coating, so it could help to the self-supportive the structure. Okay. So like I mentioned, the concept is very simple because epoxy cannot be cured. So during the printing, so we don't need to cure the epoxy. We just provide a soft layer on the outer surface. And when the material is exposed to the UV light, so the outer surface could form some hard shell. We call this cladding technology. So this hard shell, they could help form this like IPN, interpenetrating polymer network. And then the 3D structure can be formed, and then you can do any post-treatment in the oven. So here we show that that is our epoxy design, the epoxy reservoir. So we can achieve fiber volume fraction up to 65%. And with the dual cure resin coating, so we can still achieve over 55%. So this can reach aerospace grade high performance composite fiber volume fraction level. But if you guys look at other type of top prag or 3D companies, they claim they can achieve high fiber volume fraction. Normally their fiber volume fraction only contains like 20 or 30 by volume percent. Okay, it's pretty low. So that shows our printing process, and here's the cross section. We can see those dry fiber. They are fully impregnated by the epoxy, so they are very densified. It's pretty good structure. And also we are using the nano CT to study the fiber volume fraction. If you look at there, the fiber volume fraction based on the 3D data we obtained by the AI, so it's 52%. It's similar to the experimental results get from the samples. And also 99% fibers are aligned, super aligned. So that confirms this technology can print highly aligned continuous carbon fiber. And okay, so here's the performance. So where we are. So if you look at the red star, so we're over there. But still, some companies, their performance are a little bit higher than us. But we should keep this in mind. Okay, the performance of the composites actually are determined by two things: resin and carbon fiber. But we are using a kind of like low quality carbon fiber. Okay, but if you look at other type of results, they are using Torii T1100. That is a super high performance carbon fiber. So that means, based on our very rough calculation, if we can use similar carbon fiber, so our performance could be much higher, than any type of the existing 3D printed composites performance. And also, so my lab worked with my startup. So we have developed this very small top prag 3D printer, so that can print dry fiber, carbon fiber with epoxy with help of our dual cure resin coating system in between. So that shows we can print a small scale over crossing bridge structure. so there's no sagging in between. So we think that we may use this technology, for some civil, the application. So now my lab is working on this flying drone composite 3D printing systems. So we can build a small, 3D printers and attach on the bottom the flying drone. So that will enable us, to print some composite network. So this fiber, this composite could be cured by the UV from the sun, and also can be cured from the heat. Okay, so above our head. And also, when we talk about some the industry partners, so they are asking some questions. So what can you make some, what is 3D printer can make some, small parts, real for the real parts. So here is our concept. We are using the 3D printing to make a 2D pattern, and this 2D pattern can be, further stamped into a 3D structure, and by using the overmolding strategy to make it. So, but also, if you look at this composite or 3D printing area, actually, this concept is not new. Okay, 2 or 3 companies, startup companies, they already developed 3D printing, infusion, or this injection molding system. Their concept is the same, so they are using their thermoplastic carbon fiber part to make the 2D pattern, and then they do the stamping. But I think the real innovation for us is that we can print thermoset. Okay, so this type of thermoset composites can be really used in industry. It's not making toys, not using those I want to say low quality thermoplastic polymer. Okay, for some toy parts, but we can make real structural components. So here is the demonstration. So for example, if you want to print that drone landing gear, something like that, okay, so we can print a 2D structure. So this is made by the epoxy resin, okay, with a continuous fiber, with the dual resin coating. So we can form the geometry, 2D geometry, and then we can put in the mold. So this mold could be printed by other type of 3D printing method. And then we can stamp to form this drone landing gear shape. Because this is made by epoxy, and the epoxy is not fully cured, so you can imagine that they could be bendable. Okay, so once the structure is formed, then we can further increase the temperature to cure this part, okay, to make it a fully similarly curable 3D parts. So now my startup company is working on this so hopefully in the next two years, so we can make real products of this hardware 3D printing system, and also some small samples made by this type of method. So I want to thank my startup company and also the funding report. So my major grants are from the U.S. Department of Energy. So we have roughly around more than $8 million from Department of Energy to work on this type of next generation small scale continuous fiber reinforced thermoset for some vehicle application. And also, yeah, so we are looking for new opportunities. So thank you very much. Any questions?
Thank you, Kelvin. Yeah, any questions? I can run the microphone out. What will be the next level of your research? Obviously, you have the molding that's ongoing for the next couple of years, and then after that, where would you like to take it?
For the molding part, it's kind of like, in our opinion, it's easy. So we just find some company to help us build this hardware and also build the control system to make it. But I think, in the research point of view, so we also need to look at how to cure the resin fast. Because, we don't want to do any research on the resin system. Because all the resin are provided by, Huntsman, this big name chemical companies. Okay, actually, these chemicals are confidential, and they are already being certified, okay, in a lot of the applications. That's why, it's very hard to use fast cure resin for different application. But we just want to use, this certified, commercially available high performance resin and how to utilize them for our 3D printing system. Yeah, I think, this kind of study is very challenging. Yeah.
Thank you very much. Okay. Thank you, Kelvin. Thank you, everybody. You have his contact details if you think of any questions. We'll take